Hey everyone, welcome to week 3, module 3 for ME111 System Dynamics. So before we start, just some bookkeeping items here. I want to remind you that your first homework assignment, homework number 1, is going to be due on Monday, so 9/14/20 by 11 p.m. Now please reference the homework guidelines on Blackboards for details on your formatting, how it's going to be graded, the rubric, and how to submit it. Second item, we have quiz 3 for module 3. This is going to be posted on Monday as well, and this will be due Friday 9/18 by 4 p.m. So notice that there is a difference. Your homeworks are going to be due on Mondays at 11 p.m., whereas your quizzes are going to be due on Fridays by 4 o'clock p.m. So another reminder, my office hours are scheduled for Tuesdays and Wednesday mornings from 9:30 a.m. till 10:30 a.m. If you're unable to meet during these times, just get a hold of me through Teams or send me an email so we can work out a time that does work together. I have Teams installed on my phone and my home computer. I'm available most times and try to make myself readily available for your schedule needs, whatever questions you may have. The TA also has office hours as well. They are going to be Mondays. Please reference the Blackboard announcement from him to see what time his office hours are, and he'll be doing those remotely through Teams as well. So for Module 3, we're going to be covering material for modeling of rigid body mechanical systems. So objectives for this module here, once we're done with this, you should be able to do the following. Obtain an equation of motion for an object consisting of a single mass undergoing a simple translation or a simple rotation. We should be able to solve for the equations of motions when the applied forces or moments are either constants or simple functions of time. We should be able to apply the principle of conservation of mechanical energy to analyze systems acted on by conservative forces. We should also be able to apply the concepts of equivalent mass and equivalent inertia to obtain a simpler model of a multi-mass system whose motions are directly coupled. We also should be able to obtain the equations of motion for a body in planar motion involving simultaneous translation and rotation. Lastly, we want to be able to select a suitable motor and gear system for a given motion-controlled system. So this module is going to be broken down into 3 different sections. The first section is going to be Module 3-1. In this section, we're going to cover translational motion, rotation about a fixed axis. So if we reference back to our textbook, the areas we're going to be covering are sections 3.1 and 3.2, translational motion in 3.1, rotation about a fixed axis in 3.2. So our key definition here, translational motion, we have a particle is a mass of negligible dimensions. We can consider a body to be a particle if its dimensions are irrelevant for specifying its position and the forces acting upon it. One of the main things we're going to cover within this section are Newton's laws. So we're going to review these. In particular, we're dealing with equations of motion, and equations of motion involve Newton's second law. So this states that the acceleration of a mass particle is proportional to the vector resultant force acting on it and is in the direction of this force. So recall the equation F is equal to ma, force is equal to mass times acceleration. We'll be utilizing that to derive equations of motions for various problems and examples as we go through this entire module. So that leads us into the next section here, Module 3.2. We'll be covering the topics of equivalent mass and inertia and general planar motion. Referencing back to our textbook, this will be sections 3.3 and 3.4 in the text. So if we're talking about the equivalent mass and inertia, some systems composed of translating and rotating parts. Motions are directly coupled and can be modeled as purely translational systems or as purely rotational systems by the concepts of equivalent mass and equivalent inertia. These models can be derived using kinetic energy equivalence. So equivalent mass and equivalent inertia are complementary concepts. A system should be viewed as an equivalent mass if an external force is applied and as an equivalent inertia if an external torque is applied. So the last section for Module 3 is going to be Module 3.3. We're going to talk about motion control, go through some different additional examples. and a little bit of review. So in this module, we're going to go over modeling mechanical systems based on a more realistic and complex version as compared to some of the examples we've seen in the previous sections. We're also going to look at how to obtain these equations of motion for some specific applications and problems. We're talking about motion control and some case studies. We look at, up to this point right now, we've done the following types of mechanical drives. We've looked at spur gears, racks and pinions, lead screws, belts and chains, and some of the example problems and readings throughout the lectures. Things we haven't really looked at yet are worm gears, planetary gears, differential gears, and a couple other ones. So such a drive can be used to change the displacement, speed, torque, and force between our input and our output. So maybe we have an input where we need to increase the speed at the end. So we could use one of these systems for that. We may need to change the distance. We may need to increase or decrease the torque or the forces between the two.